What I would like to do is to give you an update, an overview on HPC at Intel with a certain focus on our new many integrated core architecture, but also on how it fits together into the overall picture and the framework. And as you can see here from the picture, last November we basically celebrated the 40th anniversary of the microprocessor, and it looks like a long time, but it's not really that long. And the advancements which happened during this time is pretty astonishing. Oh, that's it. Oh, okay. Turning on helps. First of all, because we will be talking about things in the future, things can change. But as far as we are planning and we know, we have a certain feeling where we want to go, we have directions and a plan. But as I said, we don't know what the future will bring. So things might change. Also, any performance claims are very likely relative, because they depend on the actual system, on the actual configuration, and even more on the actually used algorithms. So very often performance is compared using different algorithms without actually stating that. So your mileage might vary. And last not least, our software tools are optimized for Intel architecture. They are very often used on other x86 processors and systems as well. And they're working very well, generating good performance. But as I said, they are optimized for Intel architecture. So coming back to the microprocessor of 1971, which is the Intel 4004. It had 2,300 transistors, was manufactured in 10,000 nanometers, and running at 740 kilohertz. When you look at the one of the mainstream processors these days in 2011, 40 years later, for example, the Intel Core i7, it's manufactured in 32 nanometer. It has more than 2 billion transistors and running at speeds up to 3.6 gigahertz. So actually there's quite a nice advancement happening in this area. And one of the foundations is Moore's law, as we will see. So there is a myth. And the myth is that energy efficient teraflops performance on a chip can only be achieved with special hardware, software, and tools. So you need to do everything special. You need to throw everything away. Start from scratch, and then you can get teraflops performance on the chip in an energy efficient way. Well, that's certainly one approach you can take, and it's true. But we will look if it's really the only one, and as you will hopefully see, it is not the only one. It is one of many. In 2007, actually, Intel presented the Polaris R&D test chip. I don't know if anybody remembered. That one actually ran at 1 teraflop and above performance. Well, it was a pure research chip. There were only a few handful of them made because we used them to test several technologies and see how we can do it. Well, at that time, we already kind of got an idea that it might be possible actually to do it in a different way. And the way we are approaching it today is through the Intel Many Integrated Core, or MIC architecture. The design goal is to deliver general purpose energy efficient teraflops performance for highly parallel workloads using common x86 programming model, software tools, and being fully programmable. So nothing really specialized We are just basically evolving, extending multi-core to many-core. In 2011, last year, November, at Supercomputing Conference in Seattle, we showed our processor, the Knight's Corner processor, which is going to be the first commercial implementation of the MIC architecture, running at 1 teraflop double precision on DGEM. So you can actually get teraflop performance on a chip in an energy efficient way without really special hardware and software by just using mini-core technologies. And it's basically an example of Moore's laws at work. In 1997, we actually installed ASCII Red machine at Sandia Lab based on Pentium processors or Pentium Pro processors, like 9,000 plus processors, and yeah, it achieved for the first time 1 teraflop double precision performance on the INPAC. Well, a few years later, 2011, we now have a 1 teraflop double precision floating point chip running in an energy efficient way, code name Knight's Corner, and it will be the first commercial implementation. So the myth actually is busted. You do not need special hardware, special software, special programming and tools to actually get a teraflop performance in an energy efficient way. With many core technology, we think it's much easier, it's more productive, and you have seen from the speaker previously where they are playing with the development platform for this architecture, that it is pretty easy to use and very promising. So one of the foundations is actually process technology. This is an overview about some projected technologies where the industry is going. We are at 22 nanometer today. Basically, we're in the third generation of high-K gate metal, and we'll continue to evolve and invent new technologies going forward. So Moore's law will kind of continue for a couple of years. Also, Intel is very active in HPC in lots of different areas. Besides manufacturing technologies and processors, we also have Cluster Ready as a defined HPC cluster platform. We have software tools. We're doing lots of research, and we are supporting basically all the industry standards. So, besides this Xeon architecture, which you probably all know and use today, hopefully, we have introduced the many integrated core architecture to complement the Xeon processor line. But we are also working on other technologies like SSDs for I/O, also for interconnect, 10 gigabit Ethernet with and without RDMA. Recently, also by the acquisition of the QLogic InfiniBand business unit, we also now have InfiniBand solution. So that should make it interesting. And to kind of show you how the MIC architecture complements the Xeon architecture, you see that Intel Xeon architecture is based on a multi-core approach. And one of the key features of the multi-core is that we are still trying to make a single core, a single thread as fast as possible. So we spend a lot of transistors, dedicate a lot of transistors to make this happen. Very fast single core, very fast thread. Large caches, lots out of order speculation and what have you. We will certainly continue to add more cores, but in a, say, moderate way. It's not just to add cores, because that, to some extent, is meaningless, right? It also depends on how good or how fast, how slow the single cores are to get to a full solution. So Xeon is basically the working horse for HPC, as you can see in the top 500 list, and in the market in general, it's very good. We are complementing it with the MIC architecture for highly parallel workloads by extending Intel architecture basically from multi to many core. It uses a lot of threads, with wide SIMD, so it's addressing highly parallel workloads. The good thing is that the Xeon and the MIC architecture had a lot of things in common. They use the same software tools. They run a Linux operating system. You can program it in the same way you used to for parallelism. You can do it in C and C++ and Fortran. You can use OpenMP, MPI, threading building blocks, array building blocks, pthreads, what have you. So you actually can preserve your investment and still continue to get good performance on those architectures. Besides that, we just introduced the Xeon E5 processor, which is codenamed Sandy Bridge. It's an excellent processor. It has 256 AVX instruction set, very energy efficient. It's the first processor with integrated PCI Express 3 I/O technology and has a lot of other advanced features. So as I said, it's the workhorse for a very wide range of application workloads, and there are several systems already installed, and there will be even more installed based on the Sandy Bridge architecture. For example, this Yellowstone system at NCAR will have 1.6 petaflop, based on Sandy Bridge and InfiniBand. So you can still use what's available and program it in a way you're used to. Coming back to the MIC and Knight's Corner, as I said, we showed a sample of the processor at Supercomputing Conference, running at 1 teraflop double precision floating point. The interesting thing, it's manufactured in 22 nanometer. It will have more than 50 cores when it will be introduced to the market. It uses 512-bit SIMD instructions. It runs Linux, and it can be programmed in two ways. As an offload coprocessor, as you would use it similar with a GPU or a DSP or an FPGA. But you can also program it as a native network node. Because it's running Linux, you can, it's IP addressable, you can SSH into it, you can do FTP, you can NFS cross-mount, all the good, nice things you like with Linux. And it's using the same software tools and programming models and techniques. So it's basically an extension for multi-to-many core. We have a roadmap for the MIC architecture. As you already heard, Knight's Ferry is the development platform. Knight's Corner is going to be the first commercial product, 22 nanometer, more than 50 cores, teraflops performance level, and quite energy efficient, and it can be programmed as a offload coprocessor or native Linux node. It's programmed like a computer. And there will be follow-on generations coming based on the MIC architecture. Here are some of the programming models we already touched on. Fortran, C, C++, Silk Plus, which is also being supported by GCC now. Threading building blocks, we support MPI, PGAS, OpenMP. We are supporting OpenCL, Core, Fortran, what have you. We optimized libraries, and we are also working on some experimental software and APIs and models to see if we can extend it. So we basically do it hand in hand, kind of progressing with existing models and evaluating if we can add some new models as we go forward. And how you program it, basically, you use a single source code, and the compiler runtime system libraries will take care to map your parallelism basically to the underlying hardware at the time it's executing. And it could run on a multi-core system, it could run on a many-core system, it could run on a combination or on clusters of them. The real advantage is you just maintain a single source code, which I think is very good news. Here's a quote from National Institute for Computational Science at University of Tennessee. They did also tests as a former speaker on the Knight's Ferry development platform, and there's some interesting quotes that says that Most of the software does not run on GPUs and probably will never do due to cost and complexity. They tested it as a coprocessor. They tested it as a native Linux node with MPI, Global Race, Fortran, C, Python, what have you, and it all works. So it's pretty nice. There will also be a system installed going forward at Texas Advanced Computing Center, TAC, code name, the name of the system, Stampede. It's going to be a 10 petaflop system, and it's a combination of Intel Xeon E5 semi-bridge processors and Intel MIC Knights Corner co-processors. Well, going forward, I would say if you're not scared, your dreams are not big enough. You probably have heard yesterday what Intel is kind of doing in the software area for exascale in Europe by Marie-Christine. We are basically, why are people so interested in exascale? There will be a few systems around the world delivering an exaflop or an exascale. But to many other people, it is even more important to use the technologies which will be developed to build such systems in smaller configurations. So if you would assume, just assume, you can have an exaflop machine at 20 megawatt, well, you probably wouldn't be able to fit it into the new building, maybe size-wise, power-wise, it's pretty close. With this, the technologies to do that, actually a petascale, a petaflop machine would only consume 20 kilowatt. And even further, embedded systems like a mobile phone, maybe not, or a laptop, would run at a teraflop consuming 20 watt. So the interesting aspect of exascale and exaflop is also the technologies which will be developed to reach that goal and maybe have those few, maybe more exascale systems around the world, but the technologies being developed to reach this goal can be used in different other ways for quite exciting solutions. So what is Intel's plan for exascale? Well, we plan for it. It should be energy efficient. It should be quite scalable, and it's very likely to be parallel to a certain degree. So actually, we want 100 times the performance of only 2 times the power consumption of today's #1 system, which is about 20 megawatt, right? Today's #1, the K computer, is 10 megawatt, something like that, so 20 megawatt. And we'll be trying to scale today's software models forward, but also include future technologies. As we learn, when we go forward, what's good, what's working, and what's not. And we are looking at more than just the processor or programming language. We're also looking at memory and storage, at interconnect, at reliability, power management. All of those things need to fit together for an exascale solution. And we are doing quite a lot of research. We are looking at teraflops on a chip level. Oh, we basically have that today. We're looking at terabytes of bandwidth on a chip level. Oh, we are not there yet, but there are some technologies we are evaluating, and we are looking at terabits of I/O bandwidth using silicon photonics. So we are continuing to invest and research new technologies to reach those goals. As an example, at IDF, the Intel Developer Forum last year in September, we showed the outcome of a joint project with Micron Technologies called the Hybrid Memory Cube. And as you can see here, it's a die on a die, or 2 dies on a die, where you have the processor, and then you have a high-speed link to another die, so to speak, which has 3D stacked memory. And what you can reach with this is a bandwidth of 1 terabit per channel, or 120 gigabyte of bandwidth. So you get high bandwidth, Another advantage is that it consumes quite less power. So it consumes up to 7 times less energy than today's DDR3. DDR4 going forward in the future will also consume lower power, but this is an interesting technology which looks very promising. Actually, I was actually quite fast. So one last thing. It's one of my hobby project. So let's see. Are you scared now? Not yet. Okay. So because we have lots of performance, do you know what your application is doing with it? And do you know if the results are correct? I mean, computing fast is nice, but hopefully the results are right. So let's look at a little example. Those are 5 numbers. And when you add them together, you get a result, 137. It's using IEEE 64-bit double precision. So every processor, every computer supporting this will basically do that and generate the result. Okay, so those are 5 numbers. And when you do exascale computing or petaflop computing, you have lots of numbers. So 5 numbers with basically 1, 2, 3, 4 operations is not that much, right? So what happens if you do the summation in a different order? Oops. So you sum from left to right, right? So your result is now 0 instead of 137. Damn. That doesn't sound really good, right? Okay, so maybe it's just a special case, right? So do the summation in a different way. Okay, hey, we got 147. That's at least close. Close to the right. It's not the same, but it's close to it, right? So do you think it can get worse? Yes, it can. If you do it in a different way, you get -10. So not only is the result wrong, even the sign is wrong. Wow, I hope that doesn't happen with my bank account. Basically, yeah, there are different ways, and there are more permutations how you can sum the result. It actually shows you that you might need to be a bit careful when you do arithmetic on a computer, especially if you can do a lot of them very fast. Do you really know what your application is doing? And the example is from a very nice book by Mr. Coolish, a recent one, and it basically says results can be satisfactory, yeah, they can be right or almost right, they can be inaccurate, or they can be completely wrong. And neither the computation itself nor the computed results indicate which of the 3 cases has occurred. So you actually need to know, or you should know, hopefully, what your application is doing and what it does, and that you hopefully not run into such a situation that you get, say, slightly inaccurate results. And an interesting fact is that if you use parallel computing and parallel programming, you very likely hit the situation where you do a different order of operations as if you would do it serially, right? It does not mean that when you do it serial that it's the right one. It's the right way to do it. It's just one of several ways to do it, right? So the good thing is, if you experience some variations in results, it's an indication that your calculations might be a little bit unstable or ill-conditioned. right? So it's something hopefully to think about, just as a Gedankenspiel going forward. And with that, I'll thank you for your attention.